Hello everyone. Thank you for taking the time to view this presentation. My name is Asiedu and I'm a Schmidt Science postdoc at MIT Jamil Clinic and MGH Center for Ultrasound Research and Translation. Today, I will be presenting on our work to improve ultrasound penetration depth using an adversarial machine learning framework. For some background, ultrasound systems generally operate by pulsing high voltage signals. Increasing the voltage output increases the intensity of the transmit and receive signal, and a higher voltage corresponds to a higher signal to noise ratio, allowing for increased penetration. This is demonstrated by the figure on the right, which shows a schematic of penetration depth for ultrasound signals with low and high voltage. The corresponding beamformed images were shown at a low voltage of 20 volts where hypoechoic cysts at around 5 centimeters are obscured by noise and depth-wise attenuation, while the high voltage image at 70 volts provides a clearer visual of the same hypoechoic cyst at the same depth. The figure here shows what happens with low and high voltages and why adding time gain compensation is not always sufficient. Assuming we have a transducer placed on a surface and an imaging depth of D, at a nominal low voltage without the gain compensation shown by the red line, the signal strength starts off low and reaches the noise floor at a shallow depth where noise overtakes the signal. When time gain compensation is added, it boosts the signal to an extent, but it also boosts the noise. With high output voltage, we have the signal starting off much higher, and we are able to image to a much deeper region before hitting the noise floor. However, high voltage also has its downside. Firstly, prolonged exposure to high voltages can lead to thermal and mechanical bioeffects, shown in the images on the right. Thermal effects from prolonged tissue absorption of high voltage signals can cause localized tissue burn and even cause embryonic malformations in fetal imaging. Mechanical effects can cause bubbles to grow and collapse violently in the tissue, which can be detrimental. Hence, the FDA strictly regulates the maximum power output, which is related to the output voltage. Secondly, high voltage can lead to an increase in the temperature of the probe itself. This can cause malfunction in the probe electronics. The maximum temperature between the probe surface and the contact area of the body is also regulated by the FDA and set at 43 degrees Celsius. Finally, high voltage is simply not possible in certain portable ultrasound applications due to power output limits. To overcome these limitations, we propose a software-based approach with a deep neural network that can translate signals taken at a low voltage to those taken at a high voltage. Applications of our proposed solution are in achieving higher penetration depth, for example in liver imaging where a high fat layer may necessitate deeper penetration. This can also be applied to cases where there are FDA temperature and power limits, such as in fetal and ocular ultrasound imaging. And finally, can also be applied in applications that have power restrictions, such as in portable and wearable ultrasound systems. To achieve this, we look to using conditional generative adversarial networks, also known as CGANs. These are deep learning models that can translate images between different domains and have various applications in image processing, and they require paired samples of data. For example, in the image to the right, the model is learning to take a sketch of a boot as an input and generate a 3D image of the boot. Other examples are in transforming labels of a street scene to an actual real-world scene and transforming aerial images to map views. For our purposes, we collected low and high voltage image pairs using a Verasonics Vantage system with a linear array probe with 128 elements, 7.6 MHz center frequency, and 60 dB dynamic range. 363 phantom pairs were collected from a CIRS general purpose phantom, and a vascular phantom shown on the top right. For each pair, a low voltage image at 20 volts and a high voltage image at 70 volts was collected at an imaging depth of 6 centimeters and width of 2.56 centimeters, shown on the bottom right. We split the data in an 80-20 ratio, yielding 288 training and 75 testing datasets. The collected data was pre-processed for optimal training with the following steps. The first step shows the original beamformed ultrasound data on a linear scale for low and high voltage. Displaying both on the same linear scale, one can see mainly a boost in gain. There are also some near-field artifacts shown in bright white regions outlined by the red rectangle. Step 2 shows images also on a linear scale, but with the near-field artifacts removed, which corresponded to removing about 50 rows, approximately 5 millimeters of the image. We initially trained the model on these images and found that the model was primarily learning to boost gain, which is a simple problem of linear multiplication rather than to boost signal depth. So we did not stop here. Step 3 shows self-normalized image, where each pixel of the image was divided by the maximum pixel value of the image. And here, you start seeing more of the low voltage features, as well as some noise in the deeper region. On step 4, we perform log compression to 60 dB range of the images from step 3. This allows us to see the difference in signal-to-noise ratio in the deeper regions, where we do not see the bottom hypoechoic cysts in the low voltage image, but see them in the high voltage image. For the model purposes, we added 60 dB to each image and removed pixels less than 0, as shown in steps 5 and 6, since the model activation function was specific to positive data points. The images were resized to 512 by 128 for input to the model. For our model, we used a classic conditional GAN with a U-net generator and a simple CNN discriminator. We changed downsampling in the generator to maintain the column size of 128, which corresponds to the number of elements, to prevent loss of information. The generator takes an input of the low voltage and is trained to generate the high voltage image. The generated high voltage image is filled into the discriminator along with the actual high voltage image, and the discriminator is trained to determine whether the generated image is fake or real. The generator improves during training until the discriminator can no longer distinguish between the generated and actual high voltage image. Once trained, testing is performed on the test data set that the model has not previously seen, using only the generator to generate high voltage images from low voltage images. We show results for the algorithm from two representative data sets. On the first image, you see the low voltage model output and high voltage image. We pay particular attention to the hypoechoic region outlined by the red rectangle. Qualitatively, we see an improvement from the low voltage to model output, similar to the high voltage. This can be seen quantitatively by plotting a line profile through the region of interest, with the model providing a contrast-to-noise ratio improvement of 4.1 dB over the low voltage, which is comparable to the high voltage improvement of 4.2 dB. We see something similar in the image on the right, with the model providing a CNR improvement of 6.6 dB, comparable to the high voltage improvement of 6.1 dB. This slide shows two representative data sets for which the model failed. The image on the left shows a reduced signal for the lowest hyperechoic point target for the model. Here, the model may be learning to reduce tiny bright regions in an effort to reduce noise. In the second image, we also see a loss of information in structure of the bright white striations, which look blurred. This may be a result from the loss functions, which we plan to address in future studies. These plots show the signal to noise ratio or SNR and the contrast to noise ratio or CNR improvements over the low voltage input across the entire test set. And we see that the model has a comparable SNR and CNR improvement as the target. The large standard deviation bars in both the target and the model are due to the large variations in image tested. The limitations we found in our study were the loss of striation sharpness. We plan to use an updated high-definition version of the conditional GAN to address this. Another limitation is we did not test our model on in vivo datasets and plan to curate such a dataset for both training and testing the model. Additionally, we used beamformed data and believe we can take advantage of more information in pre-beamformed RF channel data in the future. To conclude, we have developed a deep learning-based approach for ultrasound penetration depth enhancement. Our approach utilizes a conditional generative adversarial network that transforms low voltage images into high voltage images. Overall, this work has the potential to improve depth-wise attenuation, overcome power limitations in portable systems, and overcome FDA limits and bioeffects. Thank you for listening.